Welcome to this explainer. Today we are diving into something absolutely fascinating. We're going to unpack the connection between the awe-inspiring optical illusions you see in nature every single day and the foundational mathematical rules we use to actually bend light ourselves. It's like nature and math are speaking the exact same language. So, when you look up at the night sky, have you ever stopped to wonder why stars twinkle, but the planets just maintain this steady, solid glow? Or how about when you're watching a sunset and the sun suddenly looks completely squished right before it drops below the horizon? Well, these aren't just random tricks your eyes are playing on you. They're actually massive visual clues that reveal the hidden physics of light acting all around us.
Here is our roadmap for today. We'll start with number 1, the atmosphere's optical illusions. Number 2, why light bends. Number 3, real-world refraction effects. Then number 4, the math of mirrors. And finally, number 5, we're going to master the mirror formula.
Okay, let's jump right into section 1, the atmosphere's optical illusions.
Now, think of our atmosphere. It's not just empty space, right? It's more like a giant, invisible layer cake made up of varying temperatures, varying pressures, and different densities. And as light travels from the complete vacuum of space down through these shifting layers of air, it actually changes speed. This changing speed literally forces the light to bend continuously. We call this really cool process atmospheric refraction.
Moving right along to section 2, why light bends. So why exactly does it bend? Well, the upper layers of our atmosphere are way less dense than the really thick air down here near the Earth's surface. Because of that, the refractive index actually decreases with altitude. In physics, there's a rule. When light passes from a less dense medium into a denser medium, it bends toward the normal line. What that means for us is that instead of traveling in a perfectly straight line, a beam of starlight actually curves toward the Earth as it comes down.
Let's see this in action. Section 3, real-world refraction effects. This perfectly answers our very first question. Why do stars twinkle? See, stars are so incredibly far away that to us, they act as tiny single-point sources of light. And as their light passes through those turbulent shifting layers of our atmosphere we just talked about, it continuously refracts, which causes the intensity of the light to fluctuate rapidly. We perceive that rapid fluctuation as twinkling. Planets, on the other hand, are much closer to us. They act as extended sources, which is essentially a collection of many point sources clumped together. All the little fluctuations from those multiple points just cancel each other out, giving us that steady, untwinkling glow.
And because of this curving light, get this, we actually gain about 4 minutes of daylight every single day. Because the atmosphere bends sunlight right over the curve of the Earth, we see the sun 2 whole minutes before it physically rises above the horizon. And it gets better, we continue to see it for 2 full minutes after it physically sets. It's literally a daily time-traveling optical illusion.
This unequal bending is also the culprit behind that squished, flattened sun you see at sunset. When the sun is sitting really low, light from the bottom of the sun has to pass through a thicker, denser slice of the atmosphere than the light coming from the top. So the light at the bottom gets pushed upward more, literally stretching and squishing the image into an oval right before your eyes.
Now, this very same principle of bending light is what creates mirages, which are driven by extreme temperature differences right near the ground. If you've ever been driving on a hot day and seen what looks like a puddle of water on the road ahead, that is an inferior mirage. The hot air near the asphalt is bending light from the sky upwards to your eye. Conversely, a superior mirage happens in freezing polar regions. Out there, the intensely cold ground bends light downwards. This can make distant objects, like massive cargo ships, literally appear to be floating up in the sky. It's wild.
Okay, let's pivot away from nature for a minute. Section 4, the math of mirrors.
To calculate exactly how light bounces off manufactured mirrors, we use a strict rulebook called the New Cartesian Sign Convention. Think of this just like a standard graph from math class. The mirror's pole, or its center, is the origin. Because incident light always travels from left to right, any distance measured to the right is positive, and anything measured to the left is negative. Same goes for height. Above the axis is positive, below the axis is negative. Pretty straightforward, right?
When you're mapping this out, you really want to pay close attention to the object distance, represented by the letter U. Because you physically place an object in front of the mirror on the left side, that value is always going to be negative. Image distance, on the other hand, flips depending on the situation. It's negative for real images that form on the left side, but it becomes positive for virtual images that form behind the mirror on the opposite side, over to the right.
And remembering this specific contrast is absolutely vital for your formulas.
Concave mirrors have their focal point in front of the mirror, on the left side. Because of that left side rule, a concave mirror always has a negative focal length. Convex mirrors, however, have their focal point behind the mirror, on the right side. Therefore, convex mirrors will always have a positive focal length.
Let's put it all together in our final section. Section 5, Master the Mirror Formula.
All right, here is the master key for optics. 1 over the focal length equals 1 over the image distance plus 1 over the object distance. It's a beautifully elegant equation that perfectly balances all 3 of those variables. But here's the catch. It instantly breaks down if you don't apply those positive and negative signs we just uncovered. If you want to solve literally any mirror problem flawlessly, you just need to follow these 3 simple steps to make sure you never drop a negative sign by accident. First up, identify your mirror type so you immediately know if your focal length should be positive or negative. Second, take a second to physically write down the sign convention for your known values. And finally, step 3, just substitute those properly signed values into the formula and calculate.
For example, let's say a problem tells you an object is placed 20 centimeters in front of a concave mirror. You do not just plug in the number 20. Your object distance absolutely must be entered into the equation as a negative 20. Forgetting that single negative sign is by far the most common mistake people make, and it will completely throw off your entire calculation.
As we wrap up this explainer, I want to leave you with a pretty wild thought. If our Earth's relatively thin air can stretch the sun into an oval, create phantom puddles on hot highways, and literally add 4 minutes to our day, just imagine what light is doing on other worlds. What kind of mind-bending optical illusions are waiting for us in the ultra-dense clouds of Venus, or deep within the thick atmosphere of a gas giant like Jupiter? The incredible math we learned today applies everywhere in the universe. Keep looking up and keep exploring.